Hey guys, today we're going to be continuing thermodynamics by looking at ideal gas processes. So, two things about ideal gas processes. We are going to assume that the amount of gas stays the same, so we're not going to add any moles, any molecules to our gas. It's going to be the same number of molecules the whole time. And the ideal gas processes are going to be defined by this equation here, which from chemistry, if you remember your old chemistry days, this is the combined gas law in chemistry. Says pressure final times volume final over temperature final equals pressure times volume over temperature initial. Important things to note here for this equation are that the pressure can be any unit of pressure and the volume can be any unit of volume, but temperature has to be Kelvin. All right, and the processes we're going to be looking at, we are going to view on a PV diagram, which is a pressure volume diagram. Here's an example of one. A pressure volume diagram has volume on the x-axis and pressure on the y-axis. And then for the third quantity that you can know for gas, the temperature, that's just going to be given right next to your little dealio guy there. And this temperature could be found using the ideal gas law, which is PV equals nRT. Should look familiar from chemistry days. N is the number of moles of the gas that you have. R is the ideal gas constant. And the other three variables we have been talking about. So each pressure volume diagram is for a specific number of moles of that gas. Here it's given as 1. We've got volume on the x-axis, pressure on the y-axis, and temperature is just given at each point. So each point here is a different state of a gas. It's just the three variables plotted as the gas at some state. All right, the first type of process we're going to look at is with a constant volume. So constant volume means volume doesn't change. So if we looked at our equation, P1 V1 over T1 equals P2 V2 over T2, or initial and final, either way. If volume is the same, both sides, then the volumes cancel out and go away, and you just have P1 over T1 equals P2 over T2, which I think is either Charles' law or Gay-Lussac's law. It's not Boyle's, but it's one of the chemistry gas laws that you should have learned in your pre-AP chemistry class or your regular chemistry class, and some chemistry class that you should have taken. So you can relate the final and the initial pressures and temperatures using that equation. And on a pressure volume PV diagram like we were just talking about, that process would look like a vertical line. So this would be the volume, this would be the pressure. If the volume stays constant, that is a vertical line. So the pressure is going to change, and then temperature is also going to change along this line. You'll have a starting temperature and an ending temperature, but the volume will remain constant, so that's what it looks like on a PV diagram there. All right, so here's an example problem with that. It says the pressure in a car tire is 30 psi on a cool morning when the air temperature is 0 degrees Celsius. After the day warms up and bright sun shines on the black tire, the temperature of the air inside reaches 30 degrees Celsius. What is the tire pressure at this temperature? And the volume of the tire is not going to change. So we'll use that equation, P1 V1 over T1, or we could say all of these are initial, equals P final V final over T final. And if VI equals VF, we just cancel those terms out. So you get pressure initial over temperature initial equals pressure final over temperature final. Now pressure here can be in any units, so we're going to leave it in PSI, even though PSI is not a metric unit. So we'll say 30 psi is the initial, divided by the initial temperature, 0 degrees Celsius. We do have to change that to Kelvin. Kelvin equals degrees Celsius plus 273. So 0 plus 273 is 273. That equals pressure final, the thing we're looking for, divided by temperature final. 30 degrees Celsius is 303 Kelvin. So here you'd say pressure final equals 30 times 303 divided by 273, whatever that number is. And I typed it into a calculator, got 33.3 psi. So a slight increase, which you would expect from a temperature increase. All right, next up is a constant pressure process. So processes with constant pressure are called isobaric. You can remember this because bar is one of the possible units of pressure, but also a barometer is how you measure pressure. So isobaric keeps a constant pressure. On a PV diagram, something that has constant pressure is a horizontal line because you've got to stay constant on the pressure axis. So the volume will change, temperature will change, but it will be a horizontal line with a constant pressure. And the equation for a constant pressure process is going to look like the combined gas law, pressure initial times volume initial over temperature initial equals pressure final, volume final over temperature final. But the pressure does not change. Pressure initial equals pressure final. So those terms go away, and you end up with VI over TI equals VF over TF, which is, I think that one's Charles's law, but it could also be Gay-Lussac's law. I don't remember, and it's not important that you know the name. So we can do the example here. It says a cylinder of gas has a frictionless but tightly sealed piston of mass M. The gas temperature is increased from an initial 27 degrees Celsius to a final 127 degrees Celsius. What is the final to initial volume ratio? So we know VI over TI equals VF over TF. The volume, we're looking for the final to initial volume ratio. So we can solve this for volume final over volume initial, which is just equal to temperature final over temperature initial. And the temperature final is 127 degrees Celsius. Do have to change that to Kelvin. 273 plus 127 equals 400. And then 273 plus 27 equals 300. So we get 400 over 300, which is 4/3 as your ratio, which makes sense. As the temperature increases, the volume should also increase. All right, and last type of process is constant temperature, which is called isothermal, thermal meaning temperature. So a constant temperature process would have an equation, PV over T, all these initial equals PV over T, all of them final. If temperature is the same both places, it just cancels out. So you get P1V1 or PIVI equals PFVF, which is Boyle's law. All right, and an isothermal compression here is when you decrease the volume, and isothermal expansion is when you increase the volume. And you should see that this is an indirect relationship. When you increase the volume, pressure should go down. When you decrease the volume, pressure should go up. And those graphs on a PV diagram should look hyperbolic, and one whole line will correspond to a specific temperature the whole time because the temperature is not changing. So like here on this pressure volume diagram, each line represents a specific temperature process. All right, so that is somewhat review from chemistry. It's just some of the gas laws. The only thing really new there is PV diagrams, unless you did those in AP Chem. I'm not really sure what AP Chem covers. But today, the crux of what we need to really look at is the thermodynamics of the ideal gas system from a work and energy perspective. And really, the first thing that you need to know is what heat and work are. So we've said before that work is force times distance, which is true, and it's a good definition for work. But work is also the transfer of energy. So if you do work on a system, then you're giving energy to the system. If the system does work on you, the system is giving you energy. Heat is a similar concept. Heat is defined as energy transferred between two objects because of a temperature difference between them. And so work is based on forces, heat is based on temperature. And really, if you look at it on a molecular level, transferring heat, which is the actual transferring energy by changing temperature, is dealing with forces on a molecular level, but we're dealing with it on a more macroscopic level, so we're calling it heat. And heat is when faster moving molecules in a hotter gas, a hotter object, transfer energy and raise the temperature of a different object that has slower moving particles. And thermodynamics deals with the flow of energy through work and heat based on the expanding gases, based on the pressure, based on the temperature, taking all of these things into consideration and seeing how the energy flows. And to take a look at that, we are going to see a piston like the one that is down here. Now we're going to say that in a piston, a gas is going to expand. And when the gas expands, it exerts a force that pushes the piston over a distance, which is doing work. So say we've got this gas in here that has a certain pressure, P. We could define the force on the piston plate. The force equals that pressure times the area of the plate. And if it moves at a distance d with a constant pressure, or a distance delta x, you're going to get that the work equals that force, P times A, times delta x. And that A times delta x is a volume. So you could say that the work done by a gas on the piston equals pressure times volume. Now, it is very important here that you keep up with which direction energy is flowing. Right now, the gas is pushing on the piston. It's doing work on the piston. So the gas is losing energy and the piston is gaining energy. The gas is doing work on the piston. Oh, and excuse me, I did slightly mess up. This should be change in volume. So work doesn't equal pressure times volume, it equals pressure times change in volume, which we see on this next slide here. And the fun thing about the work done on the system by the gas is that on a PV diagram, it is the area under the curve. So if you needed to know the work done on a gas with this diagram, the work done is simply the square area. Down here, that area would be harder to compute. You'd have to use some calculus, but it is still just the area under the curve. All right, so a couple of considerations here. In order for a gas to do work, the volume must change because the force has to act over a distance. Otherwise, no work is being done. So if it's a constant volume process where the only things changing are temperature and pressure, then that is no work. All of the energy transfer is going to be via heat instead of via work. All right, so now we arrive at the first law of thermodynamics, which says the change in thermal energy equals Q, which is heat, minus W, which is work done by the gas. And work done by the gas is energy leaving the system, which is why you have this nice minus sign. And we talked about how to write the change in thermal energy as a change in temperature yesterday. Using this equation, we derived it down from some other things over yesterday. So if you missed that, it's in the lecture from yesterday. So we could set these two things equal. We could say 3/2 nR delta T equals Q minus W, which is the work done by the gas.